All right, it's Mr. Strum again, and we're going to finish up this magnetic forces tutorial with some problems with magnetic forces. So in the homework, you're going to have to solve for the directions of magnetic forces and then use a formula for calculating the force exerted by the magnetic field of a particle. Okay, so you've seen that the direction of the magnetic force is always perpendicular to the direction of the current and to the magnetic field, as demonstrated by the Palm rule. So now we're going to figure out how large that force actually is, right? The formula for calculating that force exerted by the magnetic field of a particle is F equals QVB. F is the force in newtons. Q stands for the charge of the particle in coulombs, which is 1.6 times 10 to the negative 19th power coulombs for a proton or electron. V is the velocity of the particle in meters per second. B represents the field strength in Teslas. As the right-hand rule shows, both the velocity and the magnetic field are vector quantities, since they both have a magnitude and a direction. So treat this Q as a constant. That number will always be there in this equation. So we're going to practice right now. Old cathode ray TVs and monitors like this one here shoot electrons toward the display. They create images by deflecting the electrons with a magnetic field to light up phosphors all over the screen. Suppose a beam of electrons is moving at 5 times 10 to the 6th power meters per second. The electrons are traveling perpendicular to a magnetic field of 4.5 times 10 to the negative 2 power Tesla. What is the strength of the force acting on each electron? Well, we know Q is equal to negative 1.6 times 10 to the negative 19th coulombs. Negative because it's an electron, and an electron is negatively charged. The velocity, we were told above, 5 times 10 to the 6th meters per second. B is the field strength, which was 4.5 times 10 to the negative 2 Tesla. If you plug those values into the equation, F equals QVB, you get negative 1.6 times 10 to the negative 19th times 5 times 10 to the 6th times 4.5 times 10 to the negative 2, and you get negative 3.6 times 10 to the negative 14th newtons. The negative value comes from the simple fact that electrons have a negative charge. You will typically use a positive current and recognize that its direction is opposite the direction of the electron flow. If you point the current opposite the electron flow direction when using the right-hand rule, you'll find the correct direction of the force. Let's do another practice problem using F equals QVB. But now solve for the speed of an electron traveling in a magnetic field. Imagine atmospheric electrons in the Van Allen belt are traveling at right angles to Earth's magnetic field. These electrons experience a force of 2.5 times 10 to the negative 13th newtons. Also assume the strength of Earth's magnetic field at that point is 2.9 times 10 to the negative 5th power Tesla. Calculate the magnitude of the velocity of the electrons moving through the field. So we take F equals QVB and we rearrange it because we're trying to figure out the velocity. And if you plug everything in, you wind up with V equals 5.4 times 10 to the 10th power meters per second. To put this answer in perspective, these electrons could travel from New York to LA in less than a second. Let me get that diagram to the left there. Now we're going to do a problem on our own, and we're going to type it all out. So let's do that. All right, so what is the force on an electron in a CRT when it's moving at, the CRT would be the cathode ray tube. So we're in a cathode ray tube, and an electron is moving at 2.5 times 10 to the 5th meters per second, perpendicular to a magnetic field of 1.5 Tesla. The charge for an electron is negative 1.6 times 10 to the negative 19th coulombs. Enter the variable symbol for the quantity you need to find. Well, we're looking for F. Force. Bam. Now, select the general equation to solve for the force, and then click Done. Well, I'll just type it out. That's what we're looking for. Ta-da. Now we're going to plug in the numbers. Q. That is the charge of the electron, which is 1.6, well, negative 1.6 times 10. 10 to the negative 19th power. Well, let's do the proper formatting. There we go. Make it all look pretty. Now V is 2.5 times 10 to the 5th power times 1.5 Tesla. Thankfully, they made that one easy. If you calculate all that out on a calculator, you will get negative 6 times 10 to the negative 14th newtons. In the last problem, the electron's motion and the magnetic field were at right angles to each other. When their angle isn't exactly 90 degrees, you use the same equation, but add a sine function to account for the component of the magnetic field perpendicular to the velocity. So what this is really saying is you can still calculate the force even if it's not moving directly perpendicular to the field, but it just makes things a little more complicated. For example, a duck is flying 10 meters per second in an area where the magnetic field of the Earth is pointing towards the north at 5 times 10 to the negative 5th Tesla. The duck is flying at a 50-degree angle to the east of the magnetic field. Somehow the duck has picked up a positive static charge of 3.5 times 10 to the negative 8 coulombs. What's the magnetic force on this duck? Well, if you plug everything in and then sine 50 degrees, because that's the angle between the magnetic field lines and the charge, that's the number you wind up with. And I'll look over your homework to see if there's any weird questions like that. But here we go. So we're going to solve more problems. Part A, calculate the force of a particle with a net charge of 170 coulombs traveling at a speed of 135 meters per second, perpendicular to the magnetic field 5 times 10 to the negative 5th Tesla. So we're asked, what is the direction of the magnetic force? Well, you point your thumb in the direction of the charge, and then you point your fingers. We're using the palm rule, right? So point your thumb to the left, point your fingers upward, and your palm should be facing the screen. So the palm will be facing into the page. And then you use force equals QVB, plug in those numbers, and you wind up with 1.1 newtons. This was your Q, this was your V, and then this was your B. Okay, cool. What is the speed of a high-speed electron traveling at right angles to a 0.80 Tesla magnetic field with a force of negative 7.5 times 10 to the negative 12 newtons? The charge of an electron is negative 1.6 times 10 to the negative 19 coulomb. So here we're using F equals QVB. We're looking for the velocity. So V equals F divided by QB, and then you plug in everything. And you wind up with V equals 5.9 times 10 to the 7th power meters per second. And now we're on the summary. Hans Christian Ørsted discovered the connection between electricity and magnetism in the early 1800s. His experiment is the foundation for the study of electromagnetism, demonstrating that an electric current produces a magnetic field. When you place a charge in a magnetic field, the charge is influenced by a magnetic force whenever the charge is moving in a direction that is not parallel to the magnetic field. Use the right-hand rules to determine the direction of the magnetic field as well as the direction of the force it exerts. The first right-hand rule, or the curl rule, determines the direction of the magnetic field produced by a current. The second right-hand rule, or the palm rule, determines the direction of the force on a current due to the field. To quantitatively calculate the force of a magnetic field, we use the formula F equals QVB. Q represents the charge of the particle in coulombs. V is the velocity in meters per second. B is the strength of the magnetic field in Teslas. And that's it for magnetic forces. I hope you learned something in this lesson. And if you need any help, reach out to me in Canvas or email me, and I will help you as much as possible. But until next time, have a great rest of your day/week, and I will see you all next time. Bye-bye.